Today you will leave knowing how to recognize and draw isosceles triangles, how to prove congruent isosceles triangles using the Isosceles Triangle Theorem, how to prove the converse of the Isosceles Triangle Theorem, and connect the Isosceles Triangle Theorem to the side-side-side and angle-angle-side postulates. Let's begin. Here we have an isosceles triangle, triangle DUK. Hash marks show side DU is congruent to side DK, which is your tip-off that you have an isosceles triangle. If these two sides called legs are equal, then this is an isosceles triangle. Let us use triangle DUK to explore the parts of an isosceles triangle. Like any triangle, triangle DUK has three interior angles: angle D, angle U, and angle K. All three interior angles are acute. Like any triangle, triangle DUK has three sides: DU, UK, and DK. Side DU is congruent to side DK, so we refer to those twins as legs. The third side is called the base, even when the triangle is not sitting on that side. The two angles formed between base and legs, angle DUK and angle DKU, or angle U and angle K for short, are called base angles. Knowing the triangle's parts, here is the challenge. How do we prove that the base angles are congruent? That is the heart of the Isosceles Triangle Theorem, which is built as a conditional if-then statement. The Isosceles Triangle Theorem states, if two sides of a triangle are congruent, then angles opposite those sides are congruent. To mathematically prove this, we need to introduce a median line, a line constructed from an interior angle to the midpoint of the opposite side. We find point C on base UK and construct line segment DC. There, look at the two triangles formed by the median. We are given UC is congruent to CK because DC is a median line that cuts UK directly in half. DC is congruent to DC because of reflexive property. It is one side used in both triangles. DU is congruent to DK. This was given. We just showed that the three sides of triangle DUC are congruent to triangle DCK, which means you have the side-side-side postulate, which gives congruence. So if the two triangles are congruent, then the corresponding parts of congruent triangles are congruent, or CPCTC tells us that angle U is congruent to angle K. Now let's talk about the converse of the Isosceles Triangle Theorem. The Isosceles Triangle Theorem says, if two sides of a triangle are congruent, then angles opposite those sides are congruent. To make its converse, we need to swap the parts and adjust the wording to make it grammatically correct. You get something like this. The converse of the Isosceles Triangle Theorem states, if two angles of a triangle are congruent, then sides opposite those angles are congruent. The converse statement reads correctly, but is it true? Remember, not every converse statement of a conditional statement is true. If the original conditional statement is false, then the converse will also be false. If the premise is true, then the converse could be true or false. To prove the converse, let's construct another isosceles triangle, triangle BER. Given that angle BER is congruent to angle BRE, we must prove that side BE is congruent to BR. Add the angle bisector from angle EBR down to base ER. Where the angle bisector intersects base ER, label it point A. Now we have two small right triangles, where once we had one big isosceles triangle, triangle BEA and triangle BAR. Since line segment BA is an angle bisector, this makes angle EBA congruent to angle RBA. Since line segment BA is used in both smaller right triangles, it is congruent to itself. So what do we have? We have angle BER is congruent to angle BRE, given. Angle EBA is congruent to angle RBA, because of the angle bisector. BA is congruent to BA, because of reflexive property. That's an angle, another angle, and a side. That would be the angle-angle side, or AAS theorem. The AAS theorem states, if two angles and the non-included side of one triangle are congruent to the corresponding parts of another triangle, then the triangles are congruent. Since AAS proves these two triangles are congruent, then all of their corresponding parts are congruent. So, BE is congruent to BR. The converse of the Isosceles Triangle Theorem is true. Now you know all about the Isosceles Triangle Theorem and the converse of the Isosceles Triangle Theorem, and how to prove them.